In the last part of lecture number 3, we have discussed about how structure is important. So, we will build on that. I gave you a couple of examples of different PCs, same structure like silicon carbon, and I also give example of same material with different structures, how properties can be varying or properties can be different. So, in a nutshell, what you can say, structure consists of atomic structure, which is nothing but electromagnetic structure, and when the atoms are arranged in a particular fashion, it creates a crystal, or it can create an amorphous structure also, we have talked about it. And this crystals, when they are arranged nicely, large number of crystals we call a microstructure, and when the microstructures build on a large scale, we form a component, and components are basically formed by different kinds of processing routes like casting, metal forming, welding, powder metallurgy, machining. So, therefore, these are all connected. So, structure does not mean only one thing, it means atoms they arrange in a different way to produce a crystal, then crystals arrange in a different way to produce a microstructure, and microstructure they arrange in a different way to produce a component level structure, or I call a macrostructure. We need to know each bit of this, and we also need to know how they are connected. That is the purpose of structure property correlation. And all these things can be controlled by properties, processing. Processing determines the shape and the microstructure of any components. So, we will go deep into the microscopic structure. We already know that atoms and molecules are building blocks of any microscopic structure of matter. So, when any material solidify from a molten state or liquid stage, they tend to close ranks and pack tightly, or rather they arrange in such a way they can put them in specific arrangements. So, based on these arrangements we can have two types of structures, which is called crystalline and non-crystalline. Crystalline opposite is non-crystalline. So, we talk about that, how the atoms arrange in that way. So, let me give you first a picture which is I taken from this website astro.virginia.edu, and this is a microstructure or atomic structure of pure platinum. What do you see? You clearly see atoms are arranged in a hexagonal manner. Remember, platinum has a specific crystal structure. So, atoms from the liquid they solidify, arrange in a very nice manner and produce a beautiful structure. That is what you see here. Careful looking will tell you many things. First thing, it will tell you that if you look at this atom, there are 6 neighbors around it, right. So, that is very clear. So, this is not. So, this is the one, 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 this is the one. See, these are actually neighbors to which it is connected. So, therefore, that is the building block which is getting repeated. That is what you see in everywhere. You can see here also. Six neighbors. That is the first thing you observe. Second thing also observe, there are some blue curved region. These are the regions where atoms are missing. They are defects. We call them as a defects in the structure. Ideally speaking, if there is no defect, it would have been nice arrangement of these platinum atoms on this surface, but that is not the case. No material in this world is perfect, like all human also, we are not perfect. So, therefore, defects are omnipresent, they will be always present in a material even at finite temperature. If you look at carefully, these dimensions are very small. This is 20 Armstrong, 1 Armstrong is 10 to the power minus 10 meter. So, 20 into 10 to the power minus 10 means this distance is basically 2 into 10 to the power minus 9 meter. That means it is 2 nanometer. So, that is why you can see atoms. So, we have a device which can actually give you this kind of arrangements of atoms. So, hence it is this structure which is getting repeated and produced. So, structure in which atoms are located at regular and recurring positions in 3 dimensions are called crystalline structures. You can see these atoms are arranged in a regular manner in a 3-dimensional space. I am showing a 2D picture, but it can build on a z direction also. And so therefore, when you have this kind of arrangement of atoms, you can always define unit cell. Remember, I talked about unit cell like this, hexagonal arrangements which is getting repeated. In 3D also you can talk about unit cells. Pattern may be replicated millions of times within a given crystal. Characteristics of this structure virtually all metals as well as many ceramics and polymers. This character is present in many materials. That is why it is important to discuss. We will talk about some of the classes of metals, some of the classes of structures to give you some perspectives. First, let us talk about simple cubic arrangements. Cube is the simplest 3-dimensional geometrical structure, and it is a platonic solid because in this solid each face is made up of a square. So, there are 6 squares put together to form a cube. When you do that, you find 8 corners. As you can clearly see in simple cubic structure, only at the corners there are atoms are placed. So, there are 8 corners in unit cell. We placed each corner 1 atom. This is our way of looking at things, the top picture. But atomically, atoms will be arranged like this, what is shown here at the bottom here. So, we can connect them and form a cube, right, very easily. You can see that you can form a cube very easily. I am not drawing the back, but it can be. This is what you see at the top, and each of these corners actually having center of the atoms. That is what is a simple cubic structure. But unfortunately, there is only one metal which shows simple cubic structure at room temperature, that is polonium, very rarely observed. Why? Very simple, because majority of the space in simple cubic structure is remain vacant. So, it is very clear that this actually hardball models, and this tells you how atoms are arranged. But in reality, there may be compressible balls which can move around also. But nonetheless, structurally this is a good model to understand how the structures develop. So, here almost 50% space is vacant, only about 54% space is occupied by these metals. That is why many of the metals do not adopt this kind of structures. The next higher order structure is known as a body centered cubic structure. You have learned simple cubic. Now, let us put atoms not only at the corners of the cube, but also center of the cube. That is why it is called a body center, because it has an atom in the center of the unit cell, and because this is center of the body, that is why it is called a body center. That is the geometrical way of looking at. Actually speaking, atoms will be arranged this way. You can easily do this unit cell the way we have done. And so, this atom which is at the center, okay. So, you can clearly see that this one, remember this. So, hence you can actually generate this structure in 3D in all x, y, z directions and put together and repeated pattern and generate that. So, unit cell will have 1 atom at the body center and 8 atoms at each 1 atom each corner of the cube. So, virtually speaking, it has 2 atoms, because each of these corners are shared. We can clearly see that this atom is shared by this cube as well as this cube, correct, as well as other cubes also. So, you can put 8 cubes side by side. So, they are shared by each of the cube, that is why it is 1 by 8 by 8. So, 1 by 8 into 8 plus 1 at the center. So, that is equal to 1 plus 1, that is equal to 2 atoms per cell. But in a simple cubic, you have only 1 atom per cell. 1 by 8 into 8, that is big, that is 1 atom per cell. That is very clear. So, this is the second higher order structure. Third one is more interesting, it is called face centered cubic structures. What do you do here? What you see here, you can clearly see from this one, I am showing you only part of the atom. This is one face of the cube, okay. This is another face of the cube. So, center of the face there is atom, every center of the face there is atom, which is shown here. This is the one, this is a one, this is another one, another one, another one, back one. The 6 places 6 atoms. Along with that, you have atoms at the corners of the cube. This picture shows you the whole structure. So, how many atoms are there? So, 1 by 8 into 8, that is from the corner atoms, and remember each face is shared by another face. Okay, very clear. This if you draw this one, there is another unit cell, this will come like here. So, this atom will be shared by both the unit cell. So, that is half into 6. So, that is equal to 1, that is equal to 3. So, 1 plus 3 is equal to 4 atom per cell. That is the number of atoms in the unit cell. Okay, so that is how we can build the structures. So, all these 3 structures you see atoms are present only at the corners or at the body center position or at the face center position. Let us now look at different structure. Diamond cubic. I gave you example of diamond in the last class, right. Diamond is very beautiful glittering structure, but what is a diamond cubic structure? Well, diamond has 4-fold coordination because it is a carbon basically. So, what you have is basically face center cubic structure. You can see here atoms are at each corners of the cube and face center positions. Other than that, there are 4 atoms which are marked as a green. They are actually at the tetrahedral voids. I will show you one of such tetrahedral voids. There is one atom here. So, this is one side of tetrahedron, another side of tetrahedron. Okay. This is another side, not this one. It has to be this and this. So, this tetrahedral has a center one here, which is the central atom. This is the void. So, rather one can do many ways actually. Best one is to draw this one. Well, this is a tetrahedron, then there is a tetrahedron here, there is a tetrahedron there. Actually, there are 8 tetrahedron possible, and each tetrahedron has. So, if I draw a tetrahedron, this is nothing but a this kind of solids. It has all the 4 faces as a triangles, and this corners 4 corners at 4 atoms, and in the center you have an atom. So, this atom is 4-fold coordinated. That is what its diamond structure is. This is a carbon atom. So, that is called a diamond cubic structure. So, you can clearly see in this structure how many atoms are there, 1 by 8 into 8 into half into 6, that is come from the FCC structure, and then you have 4. So, 1 plus 3 plus 4, 8 atoms per cell, that is present there. So, this is a structure which is different for all simple cubic, body center cubic, face center cubic structure, because in those structure there is no atoms in the voids. We can create many kinds of voids, tetrahedral voids, octahedral voids, we will talk about later if time permits. See, if I have to put this thing together in one platter, how it will look like? First one is a simple cubic structure, second one is a body center cubic, third one is a face center cubic, and last one is a diamond cubic structure. So, it is clearly shown that in the simple cubic structures atoms are present only at the corners. The best example is polonium, only one metal in the periodic table, and body center cubic structures as an atom at the center of the cube. Examples are many important metals like iron, chromium, tungsten, moly. Face center cubic is even more complex. It has atoms at the each face centers of the cube, and examples are aluminum, nickel, nickel, copper, gold, silver, and lastly diamond cubic structure. It is basically silicon, germanium, metalloids. Diamond has this kind of structures. So, in the reality there are many other structures present, but they are widely present, that is what I am showing. So, another structure which is present is called hexagonal crystal structure. Atoms can also arrange in a way that they look like hexagonal unit cells. It is shown in this picture. Many metals like magnesium, titanium, zinc, alumina itself is also hexagonal crystal structure. It is a ceramic, but it is hexagonal crystal structure. So, this is important structure, not only those cubic structure, but also this. So, what is this structure? You have atoms arranged in the corners of the hexagon as well as at the centers of the two broad faces. I am going to say these two faces, hexagonal faces. These are the places where atoms are present. We also can have atoms at the center of the unit cell, but they are not at the regular positions, as you can clearly see. Actually, to be specifically, we can now generate a different unit cell, which will be better if I draw it using a green color or blue color. This is basically rhombohedron. So, this rhombohedron structure will look like this. So, you have atoms at each corner of the rhombohedron, and you have atoms at the center, not exactly center, but in the height directions. So, that is what is getting repeated. So, if you put 3 of these, you form this hexagon. That is what you have to understand. Hexagonal crystal structures are not so widely present in metals, but in ceramics many of these hexagonal crystal structures present, borides and what do I say, alumina. So, examples I already given, again reiterating. You can have chromium, iron, moly, tungsten as a body centric cubic structure, face center aluminum, copper, gold, lead, silver, nickel, very important metals are present. ACP, hexagonal close-packed structure, magnesium, titanium, zinc. So, we learned about atoms. From atoms we arrange in an order manner to create crystals. I talk about some basic crystal structure. I cannot talk all the crystal structure, then it will take a lot of time. Now, let us see how we can put these crystals together to form a microstructure. Okay, that is what will be the way to understand how we can build these crystals, we can put these crystals together and form a microstructure. So, I am talking about the body centered cubic structure. As you see here, this is a body centered cubic unit cell. So, now I arrange the body centered cubic unit cells in each of these areas in a one way. Here I am arranging this way, 1, 2, 3, 4, 5, 6. Okay. Similarly, here also, correct, but here you see it is different. It is more like this, which is getting repeated. Here it is hexagon again, here also, here it is not, here this, here also this, which one? Distorted hexagon, okay, this is a little bit distorted. So, now once I put them together one beside each other, so what will happen? They will form boundaries between them, because the atomic elements are not same in these two areas. They are little bit distorted or maybe different way arrangements of atoms are there. So, each of these actually called a similar kind of atomic elements, each of these blocks, but between them you have haphazard arrangement of atoms. So, that is why these are called boundaries. These regions are called boundaries. Why? Because they are coming in between these uniformly arranged atomic structure regions. So, these uniformly arranged structure regions are called grains actually, because atomic elements are same in this, okay, and they are separated by boundaries. That is how the grain structure forms in actual materials, and it is present in every material. Every crystalline materials will have this kind of grain structure if you look at very carefully into the microstructure. So, therefore, this is the basic unit to understand how the properties will be for a material. By knowing this microstructure, we can predict the properties. I would like to stress this upon, because we can actually read these microstructures using computer vision and then generate ML models to predict their properties. Remember, we are assuming one important aspects. We assume each of these regions are perfect crystal, that means there is no defect within each of these regions, but defects may be present also, God knows, right. Nothing is perfect in this world, but on the other hand boundaries are imperfect. Atomic elements is haphazard, there is no specific elements or atoms. You can see here it shows this green color region shows a pentagonal arrangements of atoms. Other things also possible. There is no fixed rule for the atom and arrangements of the atoms in the boundaries, they can vary. So, therefore, we see this is what is your grain structure. Now, I show on the right side actual microstructure, you can see 10 micron bar, 1 micron is 10 to the power minus 6 meter, remember that. So, 10 micron means 10 to the power minus 5 meter, that small distance is 10 to the minus 5 meters. So, now if you look at carefully, this is the grains of iron, pure iron, and in between you see boundaries, you can clearly observe that. So, that is the real microstructure, and within this each of these grains, let us talk about any of these grains, let us talk about this grain or this grain or this grain. Atomic elements will be very specifically like this, the one I showed you on the middle of the slides. So, finally, this determines size of each of the zones which you can measure. This determines the length of the boundary or the area of the boundaries. It also tells you many other features like how the grains are distributed. Sometimes each one grain has 4 boundaries, sometimes one grain has 7 boundaries, one grain has more than 3 boundaries. So, how this will affect material properties, that is very important to understand. Well, I talked about pure iron grain structure, which is very simple. That is what is this, right, that a single material, pure iron is nothing but a iron present only, nothing else is present. Yeah, there may be a little bit of oxygen, carbon, oxygen, nitrogen present, but that is okay, that is very small a quantity. So, you can see the single grain structure, all of them has grains, but single actually. But if you add little bit of carbon into iron, approximately 0.8 weight percentage, that means in 100 grams if you add 0.8 gram of carbon, that is very small quantity, whole structure will change from this to this. What you see here is two different regions, one is a white region, one is a black region. This white region corresponding to same as iron, which is seen here, these are called alpha iron, and this black regions corresponds to carbide, because you add carbon, iron carbon will react with iron and form the carbide. And in this system with iron and carbon, this specific carbide Fe3C forms very easily, and this we call ferrite. Iron is called ferrous, the ferrite, and this is called cementite. Sorry, this is a carbide called cementite. So, now we get a combination of these two, one is a carbide, other one is a iron, and this is a composite because you have combined these two, and this is the structure of steel. That is why steel is so wonderful material in this world, it provides you best properties because it has strength of carbide, carbide is a strong but brittle, and iron which is ductile. So, that is how actually microstructures can develop. So, we can create different kind of microstructures by adding different elements. This is one example I gave you. I will talk about more examples in the future lectures, but at least you understood by today's lecture that simply by playing with this atomic elements, we can create different kind of structures atomically as well as microstructurally, and these structures will have direct implication in terms of properties. So, we will talk more about these structures on this, then we will talk about properties little later. So, with this I stop this lecture 4. Thank you.